Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor IARE, Hyderabad. So in this video, we will see the tensile field beam and the complete diagonal tension. So topic will be that tensile field beams and complete diagonal tension. So just here, first tensile field beams. So field means what? Normally we are saying that a field is there, that we are going to play in the field. Means the area up to which their effect will be there. So that is called like electric field. Up to what the electric field is there, once anything we will bring to that region, it will start experiencing the force. So suppose here, okay, like this is there, or any magnet is there. Okay, so from here, this is there. This is the magnetic field, right? Now if anything is there, is here. So this will not experience any field because up to this only magnetic field is here. So we cannot say that is in the field. Once we will bring even here also, now we can say that field will affect. So because the capacity to apply the force or experience the force by this one after reaching here only. After this it will go anywhere till here it will experience the force. Again if it is not across this one, then it's not in that field. So the reason up to which their effect is there, that is called as the field. So here tension means up to what the tension will be experienced. Wing spars are typically made up of an upper and lower flange connected by thin stiffened waves. So wing spar are typically what? Made up of upper and lower flange. How it is connected? By a thin stiffened wave. So even you can see like table sum is there that at this one like this is. So here they are just putting some support, right? That is only is what? Thin stiffened wave. So this should be very stiffened, then only it will fix. If this itself will lose, then this cannot fix properly. These waves are frequently so thick that shear stresses cause them to buckle at a fraction of their ultimate load. So this should be that much thick. It's not like that you just put any small thing and this one. So it should buckle at the ultimate load only. It should not be buckle before the load. The buckle is depicted in figure A, where the wave of beam buckled due to internal. Yeah. So now this is there. So how it will get buckled? So let's say first. Due to internal diagonal compression stresses caused by shear. Okay. So here the diagonal stresses caused by shear along the surface of this one. Okay, stresses caused by shear, leaving a wrinkled wave capable of supporting diagonal. So say leaving a wrinkled wave means what happened after applying the compress, what happened? If suppose like this is there and here just after compressing this, just a wrinkle type form you can see here itself. So same way if we will compress that one and this cannot break. So what happened? This layer will get just up, it will form, or just here anything is there. Now if you will compress, okay, then what happened? There before it's getting break, this will just form like this over the skin of this one, or simply you can see here, just here. That skin right now it's just stiffened, but after compressing it's getting just wrinkles forming. So it will form, and that is called only the buckling in that case, and up to certain limit only it will buckle. Once we will apply more and it will reach to the ultimate stress, and just it will, once it will cross the ultimate one, that fracture will occur. So supporting diagonals tension only in a direction perpendicular. So just see, this is important. The tension only in the direction perpendicular to that the buckle. Okay, so wherever it will buckle, like suppose this is getting buckled, so perpendicular to that only the tension will be there. The beam is then referred to as a complete tension field. So in that case, when tension, that supporting diagonal tension is only along the perpendicular to the buckle, wherever it will buckle. So if suppose this is there, right, now this will get buckled like this. So perpendicular to this one only, that will be the tension field. Now next is complete diagonal tension. So that is just up to what the field will be there. Now the complete diagonal tension. Yes, yeah. The beam has concentrated flange area with a depth D. So here depth is D. between their centroid and vertical stiffeners spaced uniformly along its length. Okay, just we assume that beam is concentrated, flange and having depth d. The flanges are assumed to resist the internal bending moment. So what happened here, assumptions is there that whatever the internal bending moment is there because of the connection of flange and spars, right, that we are assuming is what? It can resist the internal bending at any point along the beam, while the beam of thickness T resists the vertical shear force. No, whatever the vertical shear force will be there, that can resist. Means because of that vertical force, it will not break or damage, and simply because of the internal moment, that internal bending moment, the flanges will not get buckled or break. So that we are assuming that one. This assumption has the effect of producing a uniform shear stress distribution. Because of this, what happened? Because at different point, if we will consider that one, then internal bending moment effect will be there. Now what we are doing, we are neglecting the internal bending moment and the vertical force. Because of that only we will get the uniform shear stress distribution through the depth of the web at any section. Means at any section along the depth, we will have the uniform shear stress distribution. As a result, the shear stress is given at a section of the beam where the shear force is as. So now we are taking shear force is as. So what is the stress? The stress is what? Force per unit area, right? But what is here shear stress? So shear stress is tau and force is what? Shear force is S. So S. Now area will be what? Depth is D, thickness is T. So T into D, and that is here. Shear stress equals to S by TD, force by T into D, area. Now, consider an element A, B, C, D of the wave in a figure. So now just here A, B, C, D. Element A, B, C, D of the wave in a beam panel shown in figure A. Yeah. Tensile stress sigma T are applied to the element as a result of the diagonal. So sigma T is applied here. Sigma tensile is applied here. So this side and this side sigma T is applied. Okay. As a result of diagonal tension on the plane AB and CD. So plane AB, because here, and CD, sigma is applied here, the tensile stress. So because of this, what happened? The result of diagonal tension. So because of this, here they will experience a diagonal tension like this. Depending upon what? The value of sigma T. The shear stress is and the direct stress is in, the shear stress sigma T is and the direct stress sigma is in element on the vertical plane FB. Now considering the equilibrium, okay, of the element FCD, okay, and vertically resolving forces we have, so sigma T into CD T sine alpha. So just see here, where is the this one, this H. So in this triangle, in FCD, also this is F. In FCD, in this triangle, what we can say that this is angle alpha. So CD by what we require, this one, the diagonal part, right? So this is perpendicular, this is hypotenuse, perpendicular by FC. This will be what? Sine alpha. Okay. So now from here, what? So this is the 90 degree, right? So this will be the perpendicular. So from here, what we can say? CD sine alpha. So from here we can say that FC is equals to CD by sine alpha. First case. Now this here, this is the diagonal. This is our, so this will be the, this time we are taking this FC as base. So this will be diagonal and this will be the perpendicular. So now in that case sine alpha will be equals to what? So this FD by CD. So from here FD equals to CD sine alpha. Now whatever FD is there, FD into thickness will be area of this one. FD is the length and into thickness is the area. So sigma C, so first area will be what? For this one, sigma T into FD into T equals to tau into FD into T. Okay. So now from here similarly FC. So after changing this, what we can write? Sigma C into CD into T sine alpha. First case. That is for equilibrium should be equals to tau into FD into T. Okay. So now from here what we can say? So now we have sigma T equals to tau into FD into T by CD into T into sine alpha. From this one, sigma T tau we found. Now from here, can we write this as tau into FD by CD, okay, into T by what? Sine alpha. And from figure, CD by FD is cos alpha. So from here FD by CD is what? 1 by cos alpha. So put here. So this becomes, okay, tau, oh, sorry. And one more thing. Here this sigma T into T. So this T cancel. So this T won't be there. So tau into 1 by cos alpha into 1 by sine alpha. So this will give what? Tau by sine alpha into cos alpha. So that is here. Sigma T equals to tau by sine alpha into cos alpha. Now just multiply 2 by 2. So 2 by 2. After multiplying, dividing 2 by 2. So this 2 sine alpha cos alpha is sine 2 alpha. So this will give you what? 2 tau by sine 2 alpha. This is just for simplification. If you know the alpha, you can substitute here also or here also. Just in simpler form for writing, what we did, we multiplied and divided by 2. So that now we got 2 tau by sine 2 alpha. So 2 tau by sine 2 alpha. Now, from the first equation here, tau equals to S by TD. We will substitute. So S is the load. So or you can say W is there, then W into W by TD. So just substitute this tau value here. So our equation was sigma equals to 2 tau by sine 2 alpha. Now substituting for 2 tau is W by TD, okay, by, so 1 by sine 2 alpha. That is here. 2W by TD into sine 2 alpha. That is sigma T. Okay. So now we have the sigma T value. Okay. So we resolve this vertically. Now same thing we will resolve horizontally. For the resolving force horizontally for the element FCD. Now for this FCD vertically we are resolving, because this we resolved vertically before, now horizontally. So just this will be opposite in that case. So sigma Z into FDT, one force will be there one side, the other one will be sigma T into CD into T cos alpha. Same way, just this time we have to find sigma Z. So keep sigma Z equals to sigma T into CD into T cos alpha by FD into T. T cancel. So now what is left? Here sigma Z equals to sigma T into CD by FD into cos alpha. CD by F, so FD by CD was sine alpha. Right. So this is sigma C into 1 by sine alpha into cos alpha. So this you can say sigma C into cos alpha by sine alpha. Okay. So from here, that will give you what? Sorry. This CD by FD is cos alpha. So cos alpha. So now this becomes what? Sigma z equals to sigma t into cos square alpha. Okay. So now from here, just substitute this sigma t value from here, or sigma t value from here. That sigma t is 2 tau by sine 2 alpha. So let's substitute that one. So sigma z equals to sigma t. What is sigma t? Tau by sine alpha into cos alpha. This value we are substituting. Tau by sine alpha. Tau by sine alpha into cos alpha. Sorry, tau by sine alpha into cos alpha. That is for sigma t into cos square alpha. So 1 cos alpha cancel. So now what we have? Sigma z equals to tau into cos alpha by sine alpha. So this we can write tau by what? Tau into cot alpha, or tau by tan alpha. So sigma z equals to tau by tan alpha. Now again put the tau value. The tau value is what? W by 2d. So you will get sigma z equals to W by Td into tan alpha. Right? Where since tau and sigma t are constant, because shear stress and tangential stress is constant through the depth of the beam, it follows that sigma z is also, because this is constant. Or tau is here, tau you can say that constant. Okay, sigma t is also constant, what we substituted here. So after substituting that value, sigma z will be also constant throughout the depth of the beam. Okay, so the direct load in the flange are found by considering a length z of the beam as shown in figure. So here actually this is from the figure that directly you have to take what we have taken that figure. On the plane MM, that plane axis of this, there are direct and shear stresses sigma z and tau acting in the wave together with direct load Ft and Fp. So just they again assume that force is acting Ft and Fb in the top and bottom. So Ft stands for, T stands for top, B stands for bottom of the flanges respectively. So Miss Ft force acting at the top and Fb at the bottom. Ft and Fb are produced by a combination of the bending moment Wz, force into distance. So bending moment Wz at the section plus the compressive action, that sigma z of the diagonal tension. That sigma z already we found. Taking moment about the bottom flange. So now from the bottom flange, so bottom flange, how much moment is there? Wz. This should be balanced by the flange. So that is from the top, that top flange Ft into d, because from the bottom we are taking, so bottom moment will be 0. So Fb into 0. So that's why we are not writing here that Fb into 0. For this Ft into d minus sigma z into t d square by 2. So what is here, that this is again sigma z, because in terms of force we have to write. So first is Ft into d, force into distance, minus sigma z into Td. Td we are already saying that is area, into d by 2. This will act as d by 2. So after multiplying, what we will get? Ft into d minus sigma z into T d square by 2. That is here. So in terms of force itself, but here Ft is acting, but in that place that sigma z is acting at the compressive. So in terms of compressing, but this is also the moment only. Then with moment and moment we can add, and then we can compare with the what? Bending moment. So Wz equals to Ft into d, where Ft is force at the top flange, minus sigma z Td square by 2. Hence substituting for sigma z from the equation and rearranging. Now what we got, that as sigma z equals to W by Td tan alpha. Substitute here. So after substituting, Ft equals to just here, Ft equals to W by Wz by d in plus W by 2 tan alpha. So taking this to this side, I'll just see here first. So what we have, we're finding Ft. So taking this to this side. So Ft into d will be equals to Wz minus sigma z into t into d square by and this divided by t. So ft equals to wz by d minus sigma z into t into d square by 2 into d cancel. Sigma z into t d is what? W. Right. So this is sigma z into t d. Sigma z into t d is w by tan alpha. Just substitute there. Sigma t d w by tan alpha. So here from this f t equals to wz by d minus sigma z into t into d by 2. Sigma z t d from this equation you can say that what we got? Sigma z into t d plus t d only multiplying this one equals to w by tan alpha. So same here for this we will put here. What we will get? ft equals to wz by d minus this is w by tan alpha, so w by 2 tan alpha. That is ft equals to w into z by d plus w by 2 tan alpha. So this is this one. Now resolving forces horizontally. So again, whatever the force is acting in that direction, that must be equals to 0. Now horizontally, so from the bottom part, that FB, if FB is positive, then vertically downward acting, that FT will be negative. So FB minus FT plus sigma T D, that is the force, that is must be equals to 0. Right? Which gives on substituting for sigma Z and FT. Sigma Z we know, right? And sigma T, sorry, FT just now we found. Substitute all. So now what we have to find FB, FT. So from this what we have, FB equals to this, come this side. So FT plus sigma Z into TD. FT we found, now FB we have to find. So FT, what we got FT? This is WZ by D plus W by 2 tan alpha, okay, minus W by 2 tan alpha, this comes this side, so sorry, this whole thing for this one, and plus sigma Z into T D. That will be, yeah, because from this FT is equals to FB plus sigma TZ. Yeah. So after substituting, what you will get? Because sigma Z also from that sigma Z is here. So after substituting, we will get FB equals to WZ by D into, sorry, WZ by D minus W by 2 tan alpha. So this will be the FB value. The diagonal tension stress sigma T induced a direct stress sigma Y on horizontal plane at any point in the wave. So because of this sigma T, sigma Y will be produced where? In the plane. Sigma T along the tangent it's acting, right, tensor. But now because of that, only just now I said that wrinkle will be there. So because of that, stress will produce at the surface, that horizontal plane, which we are denoting by sigma Y. Then on the horizontal plane, now we are taking at the horizontal plane. First what we have taken, we resolve force vertically, horizontally, along the sides we have taken. Now along the planes. Then on a horizontal plane SC, in the element A, B, C, D of the figure, same to the previous figure, there is a direct stress sigma Y and a complementary stress, shear stress tau as shown in figure. So see here. Sigma Y is generating here and a complementary shear stress is what? That tau. Then on a horizontal plane HC in the element ABCD of the figure, there is a direct stress sigma Y and a complementary. Okay. From a consideration of the vertical equilibrium of the element HBC. HDC for this one. The same method we have to do for that also, what we did earlier. So sigma Y into HC into T equals to sigma T into CD into T sine alpha. So now from here, right, substitute that sigma T value, what we found. here sigma t is what? 2w by td sine 2 alpha, or here t by sine alpha cos alpha. Same thing you can substitute. So substituting, after substituting, what do you get? This HC will be here. So first just here, let me see, sigma y equals to sigma t into CD by HC into t by t sine alpha. So this t cancel. So what we have? Sigma t into CD by HC into sine alpha. So that will give you what? Sigma t. CD by SC is sine alpha. So sine alpha into sine alpha. That is sigma t into sine square alpha. That is sigma y. Now substitute here sigma t value. So sigma y equals to sigma t into, sorry, sigma t only we have to replace. Okay. So sigma t only we have to replace from here. So what we got, that sigma t as tau by sine alpha cos alpha. So substitute sigma as tau by sine alpha cos alpha into sine square alpha. So a square sine alpha, what is that? Tau into sine alpha by cos alpha. That gives tau tan, sorry, tau tan. Sine alpha by cos alpha is tau tan alpha. So sigma y equals to tau tan alpha. Or from equation that, in which put S equals to W. So again we have to go back, because in starting we assume S as the force, but what we derive? W. So that S equals to W, you can just replace. So you will get sigma y equals to W by T d tan alpha. Why? Because tau is W by T d. So sigma y will be equals to W by T d tan alpha, or you can say S by T d tan alpha. The tensile stresses sigma y on horizontal plate in the web of beam cause compression in the vertical stiffness. So because of the tensile stress sigma y on horizontal plane, so now on the horizontal plane will be there, so that will what? Cause a compression in the vertical stiffener. Each stiffener may be assumed to support half of each adjacent panel in the beam, so that the compressive load P in a stiffener is given by how? So now this here, P load sigma y into TB, that area, which becomes, now put the sigma y value, what we got? Sigma y W by TD tan alpha. So after putting here WB by TD tan alpha and T, so TT get cancelled. Now what we have? WB by D tan alpha. So this is for P. What is P here? Compressive load in a stiffener. So just remember where the word is there, because we use W also as load, S also load, and P also as load. So where P is acting, where W is acting, where S is acting, that you have to take care, or else use some other. But by mentioning compression on a stiffener, compression on wave, or tensile force, so that things you have to remember. So after getting P equals to WB by D into tan alpha. If the load P is sufficiently high, the stiffener will buckle. If P will be higher, then the stiffener will buckle. Test indicates that they buckle as column of equivalent length. So that according to the experimental value, they found that equivalent length. This we had seen in the Euler's theory also, that long column and short column, that case. So if B is less than 1.5D, right, whatever the width is there, that is B should be less than equals to 1.5D, then the equivalent length will be equals to what? D by the square root of 4 minus 2B by D. This is for less than 1.5D if B is there. If B is more than 1.5D, then simply we have to take that value as D. LA equals to D. So this condition is important, that you have to remember. Even in your question bank also, one question is there related to this one. So at what, that you have to check B and D. If B is smaller than 1.5D, suppose D is 2 and B is 2.5, that is the case, because B should be what? 2 into 1.5, 3, more than 3. If more than 3 is there, so suppose, D is equals to 2. And for that, if B is more than 3, then simply you have to take D as 2. If B is less than 3, then you have to take by using this formula, that equivalent length, and then just put that one and find. Each flange act as a continuous beam carrying a uniformly distributed load of the intensity sigma yt. That uniformly distributed load sigma yt. So now here that uniformly distributed load, we are considering that as sigma yt. The maximum bending moment in a continuous beam with end fixed against rotation. So just see the maximum bending moment in a continuous beam with end fixed. So their end fixed against rotation means that end should not rotate, occur at a support and is WL square by 12, in which W is the load intensity and L is the beam. That maximum bending already by find that WL square by 12 it will be. In this case, therefore, the maximum bending moment M max occur at a stiffener and is given by Mx. M max is what? Sigma y TB square by 12. Now substitute sigma y value again. So substituting for sigma y, M max is WB square tan alpha by 12d. Midway between the stiffener, this bending moment reduced to, so midway is half of that one. Right, so that is the maximum distance. At midway, B will be equals to what? Half of that one. So this will be WB square by WB square tan alpha by 24, the half of, so midway, M max at midway will be equals to what? Half of that one. So WB square tan alpha by 12 d by 2. So that becomes WB square tan alpha by 24 d. Okay, so this will be the maximum bending moment at the midpoint. The angle alpha adjusts itself such that the total strain energy, now this angle alpha, how that will be there and on what it depends. So let's see here, the angle alpha adjusts itself such that the total strain energy of the beam is a minimum. So whatever the strain energy will be there, that should be minimum. According to that, the alpha value will change itself. If it is assumed that flange and stiffeners are rigid, this is not changing, they are fixed, then the strain energy comprises the shear strain energy of the wave only at alpha equals 2. So when this is rigid, that shear flange and a stiffener is not buckling, not moving, it's a fixed, that is rigid, then that will happen when at alpha equals to 45 degree only. So both the side it will have the same. In practice, both flanges and a stiffener deform so that alpha is somewhat less than 45 degree. But in practical, what happened? That is not rigid, it's having some deformation. So alpha is cannot be of 45 degree. If alpha is 45 degree, then it cannot deform. So usually of the order of 40 degree, that this is degree 40 degree, that alpha value is there. And in the type of beam common to aircraft structure, rarely below 38 degree. So generally it is up to 40 degree, but in case of aircraft structure, right, it's up to 38, means it's adjusted up to 38 degree, that value of alpha. For beam having all components made of same material, the condition of minimum strain energy leads to various equivalent expression for alpha. Now, how to find that alpha? For that, another formula is there. Tan square alpha equals to sigma t plus sigma f by sigma t plus sigma s. Already we derived equation for sigma t also, sigma f also, sigma s and sigma t. Just substitute that value, you will get the value of alpha, in which sigma f and sigma s are uniform direct compressive stress induced by the diagonal tension in the flange stiffener. So that already sigma f and sigma s we found. Sigma f is what? W by 2 AF. AF stands for area of flange. So 2A tan alpha, or W by 2 TD was there, right? What we derived in that TD. TD was what? Area of the flange. So here 2AF tan alpha, in which AF is the cross-sectional area of each flange. That is given here. Okay. And sigma s equals to WB by AS, that is area of this one, into D tan into tan alpha, where AS is the cross-sectional area of a stiffener. S stands for the stiffener, F stands for flange. So area of a stiffener is AS, AF is area of flange, that cross-sectional area of flange. Okay. Substituting the cross-sectional area of the stiffener. So substitute that value, whatever is there. substituting of sigma t from equation and sigma s from the above equation already we derived. Let's substitute all the value. Okay, and equation which may be solved for alpha and then solve for alpha. An alternative expression of for alpha again derived from the consideration of the total energy of the beam is, let's just substitute here the value of sigma t, sigma f and sigma s. Further, after simplifying, what you will get? 10 power 4 alpha equals to 1 plus td by, so 1 plus td by 2af whole divided by 1 plus tb by as. Right. So this will be the 10 power 4 alpha. After solving this, find the value of alpha. So see how the shear stress distribution will be there. What happened? After the compression, I told you that on the skin wrinkles will form. So see, this one is wrinkle type. Wrinkle is forming here. So this will be the shear stress distribution. So this figure is very important. So how this will bend? So bending of flange due to wave stress. Now failure stresses in plate and okay. So the previous section on the okay. So this is the final. Okay. So if you have any doubt, just comment on the video. Wait. So you can just refer the TSG action, the aircraft structure, or whatever. So refer the new one because in old some errors are there, right? So better to go for the new work. Okay, I'm just following this one, so I haven't mentioned here. Okay, so if you have any doubt, you just comment on the video and let me know so that I can clarify your doubts. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.